We will go with the next part that is related with your DRCS. Now, in this, we have next question. The minimum diameter of bar in column is. Now, I already shared you the all clauses videos, so you have to go through it. So now in column, we already know that is diameter is 12. You may have question of this from where you are mentioning this value. So we should know the clauses. That is, if we will go to clause number 26.5.3.1, then we have longitudinal reinforcement. And in this, we have different clauses. So first you can see we have 0.8% to 6%. That is longitudinal reinforcement. Preferably, we are using, they have mentioned over here, so have to be 4%, not exceed. They have mentioned over here. So we can go 4%. Critical, you can go over 4%, but preferred 4% or less than this. Then you can have here the bar shall not be less than. So here they have mentioned 12 mm in diameter. And here they have mentioned spacing of longitudinal bars measured along the periphery of the column. So students are not going to understand what spacing. So these spacing, we have these are the column bars. So we have these are the bars. And we have in this way. So spacing means this distance. This should not be greater than 300 mm. So we have this less than or equal to 300. All this spacing means all these bars. So these distances. So if we have, then we have to go for these bars. That is ties, lateral ties. The maximum pitch in helical reinforcement, we have 75. Then you can see over D, same clause number. We have helical reinforcement on the same page. 20, now here they have mentioned where the increased load on the column on the strength of the helical reinforcement is allowed for the pitch of helical turns shall not be more than 75 mm. Other are there, nor more than 1/6, nor less than 25. So 1/6 we are saying core diameter. But maximum we have 75. More than that will not allowed. Less 1/6, if comes less, we will provide that way. Then maximum pitch in lateral ties. So we have 300 mm. You can go to this clause. You can have this same clause 26.5 point something 2.1 or likewise. So now the pitch of the transverse reinforcement. So we have these three criteria. But what is maximum value? 300. We have to provide minimum of the three. Means maximum value is 300. If it comes greater than 300, then we have 300. Greater than 300, we have to go for 300. So maximum allowed is 300. Less than this is allowed. Question is maximum pitch. Minimum it is less than 300. Similarly, diameter. So we have not shall be not less than 1/4 of the diameter of largest bar. This is diameter of main reinforcement or longitudinal reinforcement. That is diameter of lateral ties or diameter of helical reinforcement. For both diameter criteria, we have this criteria. Then we have the in case of continuous one-way slab, maximum bending moment will be at. So now we have this value, a support next to end support. Now where from this we will get the answer. Now we have this. This is span moment. So we are not interested with span moment. They have mentioned it as in case of continued one-way slab, maximum bending moment will be at Oh, sorry. That we have to consider span also and we have to consider support also. So we have diagram in this fashion. So now you should be in position to draw the bending moment diagram for continuous beam. So in this portion, we have a rectangular beam. And in this portion, we have T or L beam. Okay, so one way slab. So now we have these values of coefficients. Now what is bending moment? This is coefficient into WL square. Now whatever coefficients we have given, so lesser B coefficient we have, combination of these two. And lesser that will give us maximum bending moment. This is 1 by 10. So you can see if we have value W into L square, if we have 1200 or 120, I will say. So what will happen then? WL square is 120. So now you can have, if we will go 1 by 12, then we have 1 by 12 into 120. So what we will get? 10. Then we have 1 by 16. So that will be again less. And if we will go 1 by 10 into 120, then it comes 12. Means where we will get maximum value in continuous beam at support next to the end support. Means we have, if we have diagram, then we have diagram of beam in this fashion. Here we have one support, here another, here third, here. So next to end support means we have maximum bending moment over here. So we have to use, so we have this table, don't remember exactly. So we have this table, I think table 4, 5, 6. So you can go T beam, that is continuous beam. There we have this table, and that will give us. So for continuous IS code coefficients where we are using, so we have this table, IS code coefficients. Then we can have maximum spacing of shear reinforcement is in. Now this is middle one third. Now if I will consider a simply supported beam, now we have to go for shear because you may have question and you have to explain it why. So we have this will be WU. Now if I will say this is L, then you have WUL by 2. WUL by 2. So we have shear force diagram in this mesh. So middle, I will make it 3 part. One, this will be first part, this will be second part, this will be third part. So here we have shear force large, here we have shear force large. In middle third, we have shear force less. And if shear force less, then spacing will be more. Because requirement is less, then spacing more. Means shear reinforcement required is less. Shear reinforcement required is less. Whereas in these two portions, which are first one third and last one third, shear force is large. So shear reinforcement required is more. So we have spacing less. So that is most important where we require shear reinforcement large. In the reverse, if we will go to bending moment, then we have bending moment diagram in this page. So we require flexural reinforcement. Our main reinforcement is beam. So this is in maximum in middle third. So this is flexural reinforcement or reinforcement for beam. So exactly reverse, shear force is less in middle one third and bending moment is maximum in middle one third. And therefore in beams, we are going to curtail the bar and then we are taking bars in this way. Alternately, one bar we are going to bend left support, another we are going to bend at right support likewise. Because bending moment towards support reduces. Then in a slab, alternate bars are curtailed at. Now you can go to D dash 1.4 and here they have mentioned, you can see this. Tension reinforcement provided at mid-span in the middle strip shall extend at the lower part of the slab to within. Means for continuous support it is 0.25 and for discontinuous we have 0.15. Means if we will draw the diagram, then we have this will be support. This will be next support. And we have continuous over here. Then we can bend over here. This is, they have mentioned, we have to bend it. That is at a distance which is from center of the support. And we have this value 0.15 L means L by 7. Whereas for continuous support, if I am going to bend it, then they have mentioned for continuous support, you have to bend it. That is at 0.25 L, or we can write it as 1 by 4, means L by 4. So we are going to be at L by 4. So in bottom reinforcement, these values are from center of support. But if you are going to consider at top, then your values are from face of support. Face. And that values are given 0.15 L from the support. At least 50% shall extend 0.3. Means if I will draw only support portion, then we have support is in this fashion. And then we have to draw the diagram of the reinforcement. So this is from face of the support, 0.15 L alternately. And another, if we will go over there, then it will be 0.3 L. So likewise, we have to provide. Then we have the bending moment in cantilever beam. Now draw all these diagrams. So if I will consider cantilever beam, concentrated load. I will send you a video of bending moment if possible. Then we have shear force diagram. Shear force. So it is constant throughout. If we will draw bending moment diagram, we have maximum bending moment at support, 0 at cantilever end. If I will go for UDL, so this is bending moment. Then you have this diagram. For shear force, now you have linear diagram. Then we have bending moment diagram, parabola. So you can go with the video which is in strength of material. I will try to send it. If we will go for simply supported, center concentrated load, then your diagram of shear force is in this fashion. So this is shear force. If we will go for bending moment, then you have bending moment in this fashion. Linear line. Linear. This is linear. Parabola. This is linear. If we will go with UDL, generally you will be asked these only. One question definitely you have on this. Then you have diagram in this fashion, which will be shear force, again linear. And then you have bending moment diagram. If we will draw upward, this will be tension, compression side. If we will draw downward, it is tension side. So this is parabola. So we know all these diagrams. So we have bending moment in cantilever beam is dash dash at cantilever end, 0. Then the shear force in cantilever beam loaded with concentrated load. So we have same throughout, just we have seen. So we have likewise, same throughout. Then the shear force in cantilever beam loaded with uniform. So it is 0. The shear force in cantilever beam loaded with uniformly distributed load is, now this is not option C. So we have this will be 0 at cantilever end with uniformly distributed load. So at free end it is 0. Just I have plotted this. So we have this diagram. Linear line. Just I have mentioned this. So likewise. And then we have the T beam behave as a rectangular beam of width equal to its flange width if neutral axis lies in flange. So option is B. Means if it is T beam, already we have solved the problem. Go to problems in the class notebook. And then if it is in your flange, then you will have B as BF. So equation if you will write, so Cu is 0.36 FCK XU into BF. This is value of XU. So X B will be considered as BF when neutral axis lies in flange. So these are the questions which are related with your DRCS. So now we will stop here only. Thank you.